Thank you, Dan, for that great presentation. Now I'd like to talk about an interesting new development that we are working on with Sacs called the Sacs API. Today I will talk about what the Sacs API is, what it can do, and show you a few examples to give you some ideas about how you can use it. The Sacs API, or Application Programming Interface, is a tool which can be used to programmatically interact with Sacs model files and Sacs results. This may be done by writing scripts or programs which utilize the Sacs API libraries. With Sacs 15.0 and later, Bentley provides the Sacs API as a technical preview with both Python and C++ libraries as part of the standard installation. Today I will be focusing on the Python API library, although the C++ library contains the same functionality, so if you are interested in using that language, you should be able to follow this presentation too. Before getting started with the Sacs Python API, we will need to install Python. There are a few different distributions of Python, but if you are just getting started, I would recommend either downloading Python directly from the Python website or the Anaconda distribution from the Anaconda website. The Anaconda distribution includes many additional libraries that are often used for engineering and data science, like NumPy for linear algebra and other numerical calculations, Pandas for data manipulation, and Matplotlib for visualization, among many others. They can be installed individually with the standard distribution of Python, but I find Anacondas to be more convenient. I will often use these libraries when writing my scripts, and I will be sure to point them out when I use them in any of my examples today. After Python has been installed, we still need to associate the Sacs API Python library with Python. In the upcoming release of Sacs 15.1, this has changed a bit, so I will show you the workflow for both versions. With Sacs 15.0, the Sacs API is referenced using environmental variables, which should be automatically set when installing Sacs, so no further installation is required. However, if you are experiencing issues, you should check to make sure that the paths are indeed correct. You can access the Windows environmental variables via the Windows control panel. Sacs 15.1 requires installation using the Python Package Manager, pip. Simply run the command I've shown here from the command line to compile the Sacs API Python library and install it as a Python package. This additional step has been added to give you more control over your Python development environment. With this installation method, you can have multiple versions of the Sacs API installed on different Python versions and environments. Note that if you have previously installed Sacs 15.0 and override it with Sacs 15.1, you should consider deleting the Python path environmental variable to avoid any issues. More details on installation are available in the documentation at the indicated locations if you need a more detailed reference. I also use Visual Studio Code as my development environment. If you plan on doing any extensive Sacs API development projects, I highly recommend using it. With VS Code, you get additional features like syntax highlighting, auto-completion, version control, and the ability to run your scripts directly from the editor. I have provided a link from Microsoft about getting started with Python in a Windows environment, which should help you through these steps if you need more information. Now that we have set up our environment, what can we do with this API? We can use the API for modeling and mesh generation, especially for complex geometries which don't have a specific utility to create them. The Sacs API can be used to generate those models. We can use the API for optimization by programmatically checking the results, iteratively running an analysis, and updating member cross-sections. We can have fine-tuned control over a member redesign process. We can use the API for parameterization. We can quickly generate multiple models by programmatically manipulating various parameters of an existing model file and then analyzing and comparing the ramifications of those parameters. We can use the API for load generation. If Sacs doesn't support a complex loading, you can use the Sacs API to generate the loading and apply it to the structure as member and joint loads. We can use the Sacs API for report generation and visualization. We can write custom queries to tailor our output to generate much more flexible reports than the default reports provided by Sacs. We can use the API for validation and verification. We can programmatically compare Sacs results with expected results from validation studies or hand calculations. And there are so many other things that we probably haven't even thought of. So if you have a good idea, please share it with the Offshore community on Bentley Communities, where we can help you achieve your idea and share it with others. Now let's take a look at a script to generate a simple Sacs model file. We will just be generating 2 joints, 1 beam element, its properties and boundary conditions, and 1 joint load. This is just an example to give you an understanding of how the Sacs API works and not really an intended example for you to use. Okay, so here I have Visual Studio Code open, and we're going to create a new Python script. We'll call this simple model.py. And the first thing that I need to do is import the Sacs library here. This is going to give us access to all of the objects and functions that are in the Sacs library in this Python script that we're writing. The next thing that I'm going to do is I'm going to set a model variable, and with that model variable, we're going to set it equal to a model Sacs model object. And I'm going to initialize it here, passing in a 0, which indicates that this is going to be using English units. The next thing I'm going to do is I'm going to create some joints. So my first joint is going to be model.add joint, and we're going to set the ID, which is going to be the name of the joint in the Sacs model file, as 0000. And then we're going to set the coordinates equal to 0, 0, and 0. Oops. Okay, so we've created a joint object now. We're going to set the fixity of this joint to be fixed. So that's just going to be 1s for all of the degrees of freedom. This should look fairly familiar to any of those that have looked at the text file for joint input file. And then let's see, we're going to set another joint equal to model.add joint ID equals, in this case we're going to do 0001 with the coordinates, and I'm going to just copy this so I don't have to retype it, and we're going to make that equal to 10. And we don't have to set a joint fixity for this joint object because this is going to be the top of the column. The next thing that we're going to do is we're going to create a beam element that goes between the 2 joints. So we'll call this B1. Model.add member group. Oops. Member group, excuse me. And then we're going to add a segment to this member group. So you'll see I'm setting these variables, and the reason I'm making these variables, they're not required, but if I want to reference those objects later on in the script, I need to have access to them. So here, b1.add segment, we're going to make it a tube element. And here I'm going to make something called a dictionary, pass in a dictionary to this as an argument, tube argument. So the OD is going to be 16, and the thickness is going to be 0.125. Now, all of this information that I'm going through right now is all in the documentation. So if this looks a little bit weird to you, that's okay. I really haven't talked about the explicit syntax that we're using, but this is just to trying to give you a sense of how you would write a script, and you can use this as a starting point for writing your own scripts. So then we can add the member and assign it the member group. So we're going to say model.add member from J1 to J2, and then with member group B1. Okay, and so that should be our model geometry. I'm also going to add a load to the top of the column. So we'll call this load test load, and we'll say it's going to be model.add load condition, and we'll give it a name of, say, test. And then we want to add a joint load to that load condition. So we're going to say add joint load and then apply it to the joint 2, which is at the top of the column. And here again, we're going to pass in a dictionary, which is going to have the loads applied to the element. And we're also going to pass in a load condition label. So this will be showing up as the tag for this particular load. And then we're going to say model save as, and I'm just going to call this simple model. Okay. Now I'm going to run it. Hopefully everything ran nicely. It looks like it did, so let's go into Sacs and open that Sacs model file. And here you can see our member. We have the member properties that we define. This is called B1. And here's the 16 inches, 0.125 inches for the wall thickness. The joints are 0 and 1. And if I go look at the load properties, I can see that my test load has been created with my test load ID for the joint load of 50 kips at the top of the column. Now let's take a look at a more complicated script. Here we will be generating a spherical mesh, which is commonly used for finite element verification. However, now I will be using functions with variable input to generate multiple models with different mesh densities. So here I have my spherical shell script. Now, I'm not going to write this one from scratch because it's a bit more complicated, but I did kind of want to walk through the workflow of what I was doing here to show you maybe how you would structure a more complicated script. So at the top, I've imported NumPy because I'm using some NumPy math functions. I'm importing Sacs, and I'm importing a library just to print things out a little bit nicer called rich. Here I've defined a function. So this is not actually going to execute until I call it later on in the file. So I'm going to jump down here first and show you what I'm running in my script. First, this is just a kind of standard if statement to only run this if you're using this as your main script starting point. This is just kind of a good standard practice on how to write more complicated scripts. Here I'm running a function called spherical shell, and I've created some doc streams to help it make it a little bit more clear what's going on. So here, this is going to generate the spherical shell geometry with some input parameters. And you can see up here, I have a radius, an angle, and a number of elements. And all of these have default values, but I can override them by inputting them as parameters here. And then this is going to return a tuple of joint coordinates, shell elements, joint fixities, and load conditions. And so what I've done here is I'm setting these values or these variables equal to whatever is being returned by this function. So I'm passing in here a radius of 10 and a number of elements of 6, and it's going to have an angle of 18 by default, which is going to have that opening up at the top. And then after I get all of these parameters back as values, I'm going to pass them into this generate model function, which is actually going to use the Sacs API to write out the geometry to a model file. So I'm passing in joints, shells, fixities, load conditions, and then I have some additional parameters for the shell thickness, the Poisson's ratio, and the modulus of elasticity. And so if I go back up here, I don't want to take too long on this section, but essentially what I'm doing here is I create some empty dictionaries that I can then pass back as return values. I define the surface using the parameters. So here I'm calculating basically I'm iterating over the number of elements around the radius in both directions, and I'm creating joint coordinates while I'm iterating over this. And then for each joint coordinate, if it matches up with a certain location, I've used some math here to figure out what points along in my grid of joints are on the boundaries, so I can create joint fixities and associate those with joint IDs. So here you can see I'm just adding these joint fixities to this joint fixity dictionary right here. And then I'm doing the same thing for shell definitions. I use a little bit of math to figure out when I'm on a local 0 coordinate for a shell element, and then assign the rest of the shell element definitions with these relative node locations. And so then the last thing, I just put some loads onto the joints that are at the corners of the spherical shell. And as I said, I return all those values back. Additionally, here you can see in the generate model function, I have those parameters that I pass in. I have that model object that I generate. Then I have a S1, which is my shell group, which uses the modulus of elasticity and the Poisson's ratio that I define, as well as the thickness. And then here we can loop over the dictionary of joints and assign those to the model as add joint. I loop over the fixity dictionary and add those to the particular joint IDs that are associated with those. I loop over the shell dictionary and assign those to the model. And then I loop over the load condition list and assign those. So if I run this, I can generate a model file, and it looks like it ran okay. And what I'm going to do here is, just for illustrative purposes, we'll do a 10 node element, save that and rerun it. So now if I go to Sacs, I should see 2 model files, and we'll open up the first one. So here we have our shell definition. We can see in the load properties the loads that are applied at the joints. And then I'm going to close this one down and show the 10 node or 10 element mesh. And here you can see it's a much denser mesh, but we still have the loads being applied at the correct locations, and all of the boundary conditions are still along the sides. So that's just a basic example. Obviously, this would be specific to the geometry that you're meshing, what you would have to put as parameters, but this is what I've done for this one. Finally, Let's take a look at a validation study that I did for Sacs P delta analyses. I generated a set of analyses based upon the benchmark problems from section C2 of the AISC 360 specification, analyzed each one, and compared the expected displacement results and the bending moment results with the Sacs calculated results. So here we have the verification script that I wrote. It has the import of the Sacs library. And in this one, I'm going to be importing pandas, which is, like I said, a data manipulation library. I kind of think of it as being the Python version of Excel because you can work with rows and columns of data quite easily. Again, I'm importing this rich print for just pretty printing of things. And I have this import globe, which is a Python built-in function for collecting paths that match a certain pattern, which I'll show you why I'm using that in just a second. So initially, this one has a very similar structure to the shell generation mesh, where I have my main kind of script down here, but then I have just a couple of like one function definition, and I've set up this here, which is my AISC verification data frame. So here I've set up the table essentially of my cases. So these are the various cases that I'm going to be checking. They're all here. I have just the input parameters for each one of those cases. I have the axial load, the shear deformation, which is whether or not we're using Timoshenko beams, and then the AISC moments that are reported in AISC 360, and the displacements. So those are what I'm going to be checking against. And here we have the function that gets the results from the Sacs PostView database. So this one's a little bit different because we're looking at the results. Instead of creating a model, we're going to make our model variable equal to sacs.openResultDB, and this path is going to be the path to the PostView database. So I'll see that in a little bit down here when we do the collection of the paths. And then I have my results, which are my analysis results. So this is model.analysis results. That's going to collect the analysis results, and then I can query those. So here I'm collecting in displacements, which is going to say get displacements for joint 1 for the load combination CMB. I haven't showed you the model files or the input, but I know that this joint is going to be the top of the cantilever, and the load combination is the one that I'm using for my combined axial and lateral loads. And then this order is just if I want to order the output. I'm only querying one specific load, so I don't really care, or actually the displacements for a specific load and joint, so I'm only going to get one result. So I don't really care about the order, but this is just kind of required if you want or have like a list of loads or displacements that you're wanting to query. We also have the reactions, so it's the same format, results.getReactions, and for this time it's going to be joint 0, which is going to be the base of the column, and for load combination CMB, and again we're going to say 0 order, and then I'm going to return just the moment in the x direction, or sorry, about the x-axis, I should say, for the first result. Remember I said I'd only be getting one result there. And then the displacements in the y direction for the first result. So those are the two values I'm going to be comparing against this AISC moment and the AISC displacement. Okay, so let's get into the nitty-gritty of this script here. I'm going to collect the paths and using this globe function, looking for PSVDB paths, and I'm going to recursively look through the folders. You can see over here I have all of my analyses in these folders, and it's just going to go through each one of them and look for the PSVDB file, and it's going to match it because it's matching this pattern right here. And then for each one of those, I'm going to run that function to get the results, and then I'm going to append those to these lists. And then once I get those lists of reactions and displacements, I'm going to add them to the data frame, that pandas data frame, and then I do some calculations on the list there, or the table. So I take the Sacs moment minus the AISC moment divided by the AISC moment times 100, and that's going to insert a new column for each row in my data frame. And I do the same thing for displacements. And then I have a bunch of functions from pandas that allows me to write out the to various formats. So if I write this, if I run this, it'll run through, generate a table here just in the console, but then also I have access to, say, Markdown, comma separated values, HTML, and Excel, which I can't show you here, but I could open it up in, well, let's see, here we go, in Excel right here. So that's just a way that you could look at the verification. And oh, by the way, these are really good results for the p-delta analyses in case you were curious. That's all I have for you today. Thank you all for attending, and now I'm going to hand it off to Mikkel Laos.
Thanks for watching. If you found this video helpful, please give it a like and share it with others. If you want to see more like it, please consider subscribing to this and Bentley's other channels. Thank you, and see you next time.